So following on from some of the earlier videos, we got to this stage here where we wanted to, in a way, manufacture a function such that this area here is equal to 1 as x tends to infinity. Well, at the moment, this function here, gives us an area of of root pi over 2. At the moment, this function here gives us an area of root pi over 2 as x tends to infinity. But in order for us to somehow create a function where it will give us an area of 1, we would have to get this area and then times by 2 over root pi. So in a way, to manufacture that function, we would have to get this times that area. Well, we got to this stage here where we've created this function here, and this function here, earth of x, is very useful in statistics. Now there are lots of other functions similar to that. So here's another one, and here's another one here. So in this video we are going to look at this one here. Okay, and there are other ones as well. So when you get given a strange function like this, you see these okay, when we're given a complicated function like this, all that we can do in our minds is to visualize the derivative. So hang on. So when given a complicated function like this, all that you can do in your mind is to visualize this derivative graph, and then somehow slowly work backwards to create this function here. Okay, so all that you can do when given a complicated function like this, all that you can do is visualize the derivative graph. And once you've got your derivative graph, slowly somehow work out the original graph. Okay, so let's have a look at this one here. First, we have to try and understand this bit here. So hang on. So we are now going to try and visualize this graph here. But before we can do that, all that we can do in our minds is to visualize the gradient, the derivative graph, and then from the derivative graph we can work out the original graph. But first we need to try and understand this. Now let's try and visualize in degrees as opposed to radians. So instead of working radians, let's just pretend to work in degrees. So sine of x in degrees will be 1 cycle in 360. Well, if you have sine of a bubble, well, if you square this, it will well, the point that I'm trying to make here is that we are trying to understand this bit here. You see, the normal sine of x, you have 1 cycle in 360. Well, when you have squared, when you have squared here, you're going to have this over 360 many cycles. The point that I'm trying to make here is that the normal sine of x, you're going to have 1 cycle in 360. But when you have squared, sine t squared, you're going to have so many cycles. You're going to have so many cycles within the 360. So sine of x will look like this. Sine t squared you're going to have so many cycles in here. So hang on. If you get a graph plotter and plot this, hang on. So this blue line here is your normal sine of x. So this is 0. 360 is somewhere out there. But this is not even 1 cycle yet. But the red line, you can see you're going to have so many cycles in before you even get to 360. So the point I'm trying to make here is that your normal sine of x will look like this, 1 cycle. But sine squared of x you're going to have so many cycles in here. So in order for us to understand this, we now understand this part here. So hang on. So now let's look at this. Bear with me. So so looking, hang on, bear with me. So looking at this, looking at this here, our normal sine of x, will be one cycle here. But because we've got one t squared, we're going to have so many cycles in between. But remember, when we are looking at it in terms of this function, we are really looking at it. We are really looking at the area from 0 to x. So bear in mind that we are looking at the area of the derivative. So hang on, let's start again. When given a complicated function, all that you can do is visualize the derivative graph. Now, once you've got your derivative graph, we can slowly work backwards to find out our original function. Okay, so now what we've got is the derivative graph. Bear in mind that, well, the derivative graph, when looking at the derivative graph, you're looking at the area from 0 to wherever x may be. X can slide back and forth. So we are looking at the area. Okay, we are looking at the area from 0 to wherever. So looking at this here, bear in mind that this area here is bigger than this area here. Okay, and this area here is bigger than this area here. Just bear this in mind, and bear in mind that this area here is bigger than this area here. So from this, your original function will look something like this. Because from here, let's say this is a, then well, the point here is that, hang on, the point here is that, hang on, the point is that this area here is big, and then you're going to have a minus area, so you're going to decrease your area by a smaller amount, and then you're going to increase your area by a smaller amount than this amount, and then you're going to decrease this area here where it's smaller than this amount, and so on here. So your graph will end up looking like this. Okay, bear in mind that this here is an even function. Okay, because if you stick a minus version into this thing here, it will be the same as, well, this here is an even function, so it will look something like this. Okay, but don't forget, this area here, even though you might think, so your graph, your s of x will look something like this. Hang on, and it will look something like this. Now you might be wondering, well, this is a positive area. Why is it going downwards here? Well, if you think about it, if you look at this here, let's just imagine that this here is at negative 3, and this here is, let's just imagine it's positive 3. The area from this area here is from 0 to 3. Now this area here is from 0 to negative 3. Well, in order for us to really evaluate this, we would need to switch these two around. So that would then give us from negative 3 to 0. But then when we switch these two around, we have to obey one of the laws where we have to stick a minus in front. Well, this here is this area here. It's a positive area here. And then, but you've got a negative there, making the original s of x to be negative. Okay? Yeah. Okay.